Hello friends, I am En-RZT and today we are going to study third order shear deformation theory for laminated composite beams. So let's start. So in the previous lecture we have studied the classical laminated theory for the beam, and then also we have studied the first order shear deformation theory, and today we are going to study the third order shear deformation theory. So we will study this theory today, inshallah. So now we are going to start. So first of all, for the third order shear deformation theory, if we see, we write the in-plane displacement fields as follows: u naught x plus z times theta x plus z square times psi x plus z cube times phi x. So we are taking up to the cubic variation. Okay, the in-plane displacement higher order is cubic, and the transverse displacement w of x is w naught of x. So it's a constant. Okay, there is no stretching allowed. So now if we write the shear strain part, gamma xz, that is equals to del of u of xz by del z plus del w by del x. Okay, so if we differentiate this with respect to z, so this would be 0 and this would be only theta of x. So theta of x plus the derivative of z square is 2z times psi x plus this z cube derivative is 3z square phi x plus then derivative of the del w of xz. So we know that this is nothing but w naught of x. So it is del w naught by del x. So we are having this shearing strain. Now applying this shear stress, that is the transverse, basically we should mention the transverse shear stress and the shear strain free or 0 at the top and bottom surface. So if we apply this boundary condition that at the top and bottom of the beam the shear stress or strain is 0, so this at gamma xz at z equals to plus h by 2, that should be equals to 0 at the top, as well as gamma xz at z equals to minus h by 2 should be equals to 0. If we apply these conditions at top and bottom shear free criteria, then we will get theta x plus 2 into h by 2 psi x plus 3 into h square by 4 into phi x plus del w naught by del x equals to 0. So what we have done, we have just replaced z, the value as h by 2 plus h by 2 at the top. Also here z square as h square by 4. Then at this position we are having theta of x minus z equals to, we are considering minus of h by 2 at this position. Okay, so we know that shear strain is this. We got this as a shear strain 2z and z square. So just we are replacing z as plus h by 2 and plus h by 2 whole square, and at the bottom interface we are having minus h by 2 and minus h by 2 whole square. So if we take this, would be plus h square by 4 again. So we have just placed these things. Okay, h square by 4, h square by 4, and it is plus h by 2, it is minus h by 2. So after adding or subtracting the equation, so we can see, so this is the equation 4 and this is equation 5. So if we add and subtract, so we will get psi of x equals to 0 here, and by adding the equation 4 and 5 we are having this phi of x equals to this. So we get phi of x in terms of theta x and del w naught of del x. So finally we are getting the displacement field in plane displacement u of xz as u naught of x plus z times theta x minus 4z cube by 3h square theta x plus del w naught by del x, and w of x is the same w naught of x. So how many unknowns are there, we can say? So we are having u naught of x as unknown, theta of x as unknown, and w naught of x. Okay, so we are having only 3 unknowns now. So in the previous one, in the equation 1, how many unknowns we were having? We were having u naught x, theta x, as well as psi x, but psi x and phi x. So now we are having only here, as you see, instead of 5 we are having only 3 unknowns. Okay, now we will write the epsilon xx strain, that is del u by del x. Okay, so if we put the value of del of u of xz as del u naught of by del x plus z times del theta x by del x and minus of 4z cube by 3h square into this, then the variation of this epsilon xx will be nothing but del of u of xz by del x, that is del of del u naught by del x plus z times del of del theta by del x minus 4z cube by 3h square del of del theta x by del x plus the derivative of the variation of transverse displacement. Now we will have the transverse shear strain as 1 minus 4z squared by h square theta x plus del w naught by del x, and the variation would be written in the same way, just applying the variable. Now we will get the stress. So before this we are having this strain part. So we got the strain displacement relation. This is the strain displacement relation. Strain displacement relations. Okay. And now we are having stress strain relation. Stress strain relations using the constitutive equations. So these are the constitutive equations. Okay. So we are having a stress as material properties times the strain, and strain we have written this. Okay. Similarly, sigma x equals to this constitutive equation times the shearing strain. So this is the real properties and this is the strain part. Now we know the virtual work principle, that internal work done is nothing but variation of the strain times stresses. So it's variation of the strain into sigma xx into this shear strain part into sigma xz, and it's integrated over the whole domain. So now along the y-axis if we integrate, we get the thickness of the beam as b. So if it is our beam, okay, so we are having this as x and this along y, and suppose this as z. So we are having this along y direction as a width b. So if we integrate along y, we get this b. Okay, and x and z are there. Okay, so now we will open this del of epsilon xx. Then first part would be this, then the second part of that strain would be this into z, and then the third part of this would be this part into the strain into stresses. And then if we open this variation of the shear strain gamma xz, then we will have this part multiplied by del of theta x plus variation of transverse displacement derivative. Okay, now if we just further integrate this part, okay, because it's a function of z only, it's a function of z integrating this, and here it's a function of z and z, and these are the function of x only. So this is kept outside the integration of x, and then it is only of the z part. This is only integration of the z part. This is only integration of the z part. It's integrated with respect to z, and this is the integration of the z part. So this slide we will see that, okay, the integration of this we are getting as nxx. Okay, del of del u naught by del x into nxx. Then this would be the same here. Okay, and this integration of this would be mxx, that is the z times sigma xx, that is the moment mxx. And then if we integrate this part with respect to z, we will get pxx into this, and plus if we integrate with respect to z, this we are getting as x sxz minus rxz. Now we will see individually that external work done is nothing but variation of the transverse displacement times the transverse load acting. So now this del of w net work, virtual work done, that is internal work done minus external work done, a variation of that should be equals to 0. Therefore 0 equals, we are having this. So now if we take the integration by parts, okay, so finally after integrating by parts we get this. So we are having del nx by del x into del u naught of x, del mxx by del x into del of theta x, del pxx by del x into del theta x, minus del 2 pxx by del x square into delta w naught of x into del of theta x into sxz minus del theta of x into rxz, and minus of del of sxz by del x into del w naught x plus del rxz by del x into delta w naught x. Now After taking the coefficient, collecting the coefficient, first we will take del of u naught of x. So in plane displacement u naught of x, if we take, then only del nxx by del x should be equals to 0, because no another part would be there, only this part is there. Okay. Now if we say del of theta x, then we are having this del mxx by del x plus del pxx by del x plus sxz minus rxz equals to 0. You can see from here del theta x, this is the part, so first part is here. Then del of theta x is this, so this part is also there. This is the del of theta x, so sxz is also there, and rxz. So we can see all four parts are there. Okay. Now we will collect the coefficient of w naught of x. So let's see, w naught of x is where. So this is the w naught of x. So del 2 pxx by del x square should be there, and this is the w naught of x, and this is also w naught of x. So we will see w naught of x is having del 2 pxx by del x square plus del x sxz by del x minus del rxz by del x equals to q naught x by b. So we are having this three governing equations. So where we know that n(xx) was nothing but integral of sigma xx into dz. So if we integrate for the laminated composite beams, so we know that throughout the thickness of the beam there are many layers. So from layer 1 to layer 2, layer 2 to layer 3, and so on, we are going to so interface 1, Z1, Z2, Z3, Z4. So one to another we just integrate. Okay, so k equals to 1 to n layer, we are integrating. Okay. So now if we just open this sigma xx, so it would be q11 times epsilon xx and q11 k into dz into, if we open this epsilon xx, then the first part would be del u naught by del x plus z times del theta x by del x plus 4z cube by 3h square times this part. Okay, so we have just opened and multiplied with q11 of k. So we get this integration as a1 times del u naught by del x plus b1 times del theta x by del x minus c1 times this. Okay. Similarly, mxx is nothing but integral with respect to z into sigma xx. So if we open in the same way, we will get b1, d1, and e1. Then now pxx, which is nothing but multiplying this 4z cube by 3h square with sigma xx of k and integrating with respect to z. Then we will do the same, and after integrating we get c1, e1, and g1. Okay, and for the shear part we get sxz as integral of sigma xz dz. So we are getting this 244k into this, and this we named as ASH. Okay, and for rxz we are multiplying this 4z square by h square into this, and we are getting this as a VSH. So now in matrix form we can write nxx, pxx, mxx, and pxx as this a1, b1, c1 matrix, and this displacement vector in this form, derivative of that. Similarly, the shear part or shear force we can write in this way: sxz and rxz, ASH into 0 and VSH into this. So now finally what we will do, we will just keep this equation 24 and 25 in equation 18 of the governing equations, and just we will put the value of, suppose, minus del by del x of nxx. So nxx value what we are having, a1 times this, so we can keep here as a1 times del of u naught of x by del x plus b1 times del of theta of x by del x minus c1 times what we are having, del of theta x by del x, del of theta of x by del x plus del 2 of w naught of x by del x square. Okay, so if we just take the derivative of this, so we will get a1 minus of a1 into del 2 u naught of x by del x square minus b1 into del 2 of theta of x by del x square minus plus C1 into del 2 of theta of x by del x square plus del 3 W naught of x by del x cube, and so on. So in this way we will just keep another one, the second governing equation and third governing equation, and we will get in this way, and finally we will solve this value. Okay, so we will get that results. So now we will just see the code. So we will just run this code again. So let us see what is the higher order shear deformation theory, or how we getting the in-plane displacements and shear strengths in the stresses. So let's see. First of all, if we see, we will start with the in-plane displacement first and transverse. So first of all, we see the transverse displacement, that is a constant throughout the thickness, because W of xz was nothing but W naught of x. So throughout the thickness, the transverse displacement was kept constant, so it is constant. Now we will see the in-plane displacements. So we can see in-plane displacement now, it's no more linear, but it's a cubic variable. Okay, so it's getting warped, and it is showing that it is just varying in a higher order way. Okay, not linear but a cubic fashion. Okay, so this is the higher order shear deformation theory, or we can say the warping or in-plane displacement is cubically varying. So plane section is no more plane, it is now warping in this cubic way. Okay, now we know the third figure is showing the shear strain, that is at top and bottom it is satisfying the zero criteria. Okay, that at top and bottom the shear strain is 0. Okay, and it is quadratically varying throughout the thickness of the beam. While it's violating at the interfaces lamina, we will discuss that later. And from the constitutive equation we can see that this is the transverse shear stress sigma xz. Okay, so at top and bottom shear stress is 0, and it's varying quadratically, but it's violating the continuity conditions, as shear stress must be continuous at the interface, because it is the first layer and it is the second layer. So at the second layer it should be continuous, and with the third layer it should have the continuity, but we are seeing that it is showing a jump. So this is the drawback of the third order shear deformation theory, that from the constitutive equations we are not getting the shear stress as continuous. Okay, now this figure, what is showing, it shows the shear stress sigma xz that is continuous throughout the interface or lamina thickness. So this we obtain by integrating the equilibrium equations. So from integrating the equilibrium equations, we are getting this results. So we get this higher order or third order shear deformation theory. So thank you.